I am Ravindra from AAA department, and we are dealing with 4th unit in HVDC transmission systems. And in the 4th unit, this module is of 3rd module. That module consists of source of reactive power, synchronous condensers, static VR system, and STATCOMs. This is the module 3rd which we are going to deal. Here what we are going to discuss here is sources of reactive power, that means through synchronous condensers, static VR systems and STATCOM devices. Now at the end of this lecture, student will be able to know the sources of reactive power, mainly the synchronous condensers, static VR systems and STATCOMs. Okay, we are going to learn these 3 devices: synchronous condenser, static VR systems and STATCOM device. These 3 devices will be clearly demonstrated now. Okay, let us consider synchronous condenser first. What is a synchronous condenser and how it can generate the reactive power? Okay, what is mean by generally reactive power here? When in the generation process, we have active power as well as reactive power. S is nothing but equal to P plus S is nothing but equal to P plus JQ. Totally we call it as complex power, right? Or we can call it as S is the apparent power. Totally we have with active power as well as reactive power. Q is nothing but reactive power, P is nothing but active power. Whatever the actually the utilization is main active power. At the end point, whatever we are consuming is active power. Then what is the reactive power? What it is, why is it necessary? Because here without reactive power, the active power cannot be transmitted to the end point. There is necessity of this reactive power to maintain the voltage constant throughout the transmission. It is very important here. The necessity of this reactive power is to maintain the voltage throughout the constant. There is necessity of this reactive power. Without reactive power, the active power cannot be transmitted through the other end or the other load point. Here mainly, suppose if we consider that means here actual consumption is active power. That means here to receive the active power at the end point, there should be a reactive power compulsory. That is the main important here. Now to generate that reactive power, what are the devices we are using? Last class we have discussed about AC filters, shunt connected capacitors. We have connected AC systems, AC main system we have considered. 3 types we have considered. Now let us consider remaining 3. Here in this one we have synchronous condenser, we have what we call it as synchronous capacitors. It acts as a capacitor also. Okay, and let us discuss this synchronous condenser in detail. And we have another STATCOM device we have. These devices let us discuss in detail about. Now let us consider the synchronous condenser. What is the working principle of the synchronous condenser? When the synchronous motor is operated at no load, let us consider it is operating at no load condition. That means we don't apply any load. That is at no load, the synchronous motor is operating. Let us consider that no load. Let us put as no load. It is operated at no load under overexcited condition. When it is operated under overexcited, that means generally the motor will be operating at rated speed. That is let us consider in our laboratory systems, in our what we have in our labs, we have a motor having rated RPM as 1500 RPM. Let us consider in the type of example. When we consider it is over-excited, means that motor will be rotating above the speed of 1500 RPM. Okay, suppose rated speed is 1500 RPM. Over-excited means that the motor will be excited more than 1500 RPM. That means the speed is more than rated speed. If it is overexcited condition, that in that condition, that condenser, whatever the synchronous motor, acts as a static capacitor. It behaves as a static capacitor. Okay. If that motor, that synchronous motor is operating in that condition, that is overexcitation condition, then we can call it as synchronous condenser. We can call it as synchronous condenser. Then how this happens? What is the lagging power here? What is the leading power here? In what cases it is there? Now let us see here. When the excitation of the synchronous motor is increased, suppose excitation of the synchronous motor is increased, okay, over excited, that means above rated speed, that is above rated speed, it takes a leading current here. It takes a leading current here. That is when the machine is over excited. In that condition, here that voltage is EMF generated will be greater than the terminal voltage V. Here the voltage whatever is greater than the terminal voltage V here. That is we can consider E is greater than the terminal voltage here. Okay, that means in this condition the drawing current from the main supply will be very minimum. The current when this generated EMF is greater than the terminal voltage, then in this case whatever the current is drawn from the supply will be minimum case. That will be minimum case. Okay, in this condition we call it as a synchronous condenser. The motor when it is operated and over excited condition, in that case it draws leading current, that is in that case E will be greater than the terminal voltage here, and whatever the drawing current from the AC main supply will also minimum. In this condition that motor which is operated under over excited case is considered as synchronous condenser. Synchronous condenser. Suppose if the motor is under excited, that means it is operated under the rated speed 1500 speed. If it is under excited, that means it is operated under rated speed. In that case it draws lagging power. Here it draws lagging power from the circuit, and the power factor of the machine will be lagging in nature. It draws lagging power factor in the circuit, and the power factor of the machine will be lagging in nature. In that case, in the previous case, and when it is over excited, the power factor will be leading. When it is under excited, the power factor will be lagging. Right? This is the case here. That means when the motor is over excited, the power factor will be leading. When the motor is under excited, the power factor will be lagging in the case. Okay, and if the motor is over as it takes the leading power from the circuit, the power factor would be leading in nature, and this phenomenon is known as This phenomenon is the working of the over excited synchronous motor, and this is called as synchronous condenser, or we can call it as phase advancer. We have the three names here. You can call it as a synchronous condenser, phase advancer, right? Now let us in detail study with phasor diagram. Let us in detail study the synchronous condenser with some phasor diagrams. Now let us consider one practical example here. Let us consider an industrial load here. We are considering a practical example here. An industrial load driven by induction motor. An industrial load driven by induction motor. That means here mainly the reactive component acts. That means here the industrial load is driven by the induction motor. Here the induction motor means generates it absorbs the reactive power. It consumes more reactive power, right? Induction motor itself consumes more reactive. That means here the reactive power requirement is there here in this case. And also lightning and heating loads supplied through the transformer. And lightning and heating loads supplied through the transformer also requires most reactive power. It requires reactive power. Okay, whatever the loads here considered, lighting loads and induction motor loads, that are industrial loads, we consider consume more reactive power, right? Now let